Japan built a wall most people on Earth have never heard of. I want to explain exactly what it is, how it was built, and why every single detail matters. Here is the basic fact. Japan constructed a seawall running 400 kilometers along its northeastern coastline. That distance is roughly the same as New York to Boston and back, twice. The wall stands taller than a 4-story building. It cost $12 billion, and it took over a decade to finish. When I first looked at those numbers together, I had to stop and think. This is not a small flood barrier. This is the largest coastal defense structure ever built by any country in human history. The reason it exists comes down to one date. March 11th, 2011. That is when a massive earthquake hit off Japan's coast. The ocean floor moved 50 meters in roughly 3 minutes. That rupture displaced 500 kilometers of ocean water all at once. What followed was not a single wave. It was a moving wall of black water, sometimes 40 meters tall, traveling across Japan in 30 minutes. Nothing in its path survived. In that single hour, 90% of Japan's existing seawalls failed completely. Nearly 20,000 people died. The country watched in real time as billion-dollar infrastructure collapsed in seconds. The world's largest breakwater at the time, which cost $1.6 billion to build, was destroyed almost instantly. What engineers noticed was critical. It did not break from the front. Water topped it, ran down the back face, eroded the foundation from behind, and the whole thing vanished. That is the engineering problem Japan had to solve. Not just how to build a bigger wall, how to build one that does not fail the same way when water goes over it. So they started studying every single failure. Before one new stone was placed, teams demolished the old walls and examined each failure mode in detail. The way I understand it, this step alone took months. Engineers needed to know exactly how the old walls died before they could design something better. Now here is something that genuinely surprised me. Most of this new wall is underground. Only about 14 meters shows above the surface. The full structure goes 25 meters below sea level in some places. Engineers modeled the wall more than 200 times in computer simulations before placing a single stone on the actual coast. And the wall height changes every kilometer. Taller on exposed headlands where waves hit hardest. Lower in sheltered bays. Every measurement came from real wave data collected from that specific stretch of coastline. This is not a flat uniform structure. It is a living response to geography. The construction was split across 440 separate teams, working simultaneously along the 400-kilometer route. That scale is hard to picture. If even one of those teams went bankrupt mid-build, a gap would open in the wall. A gap means a death trap in the next tsunami. So zero tolerance was the standard from day one. Every single section had to be finished. Before any digging started, survey ships drilled the seabed along the entire route. What they found underneath was different almost every kilometer. 3 distinct foundation types: soft clay in some zones, dense sand in others, hard rock in others. Each one requires completely different engineering underneath. You cannot just pour the same foundation everywhere and hope. The ground tells you what it needs, and you must listen. The building sequence is something I find genuinely impressive. First, 400 kilometers was measured meter by meter before a single machine started digging. An entire coastal pine forest was cleared, and erosion matting followed the bulldozer within minutes, always. Because exposed soil on a coastline disappears fast. In the clay zones, the ground was too soft to even support a bulldozer's weight. The machine would sink, so engineers used steel road plates spread across the surface. The machine floats above the mud. Simple, effective, problem solved. Then came foundation work. They were building 25 meters below sea level in an active surf zone. The tide gave construction teams only about 4 hours every day on the seabed. Every minute was counted. Divers guided 5-ton boulders into position underwater by hand, in the same ocean that had just destroyed the coastline. Engineers checked progress using sonar because visibility was zero. They could not see the work. They had to trust the data completely. To me, that is one of the most demanding engineering environments I can imagine. Between the boulders and the fill material sits something called a filter layer. It sounds small. It is not. Miss the filter layer and fine soil particles slowly migrate into the rubble mound over years. The wall bleeds away from the inside without anyone seeing it. That filter layer works silently, forever. After weeks of underwater work, the rubble mound eventually breaks the sea surface. A membrane called geotextile goes over it next. Its job is to stop fine soil from moving through. Then every layer of fill material gets compacted using heavy rollers. The slope angle is exactly 1 in 5, steeper than that, and boulders slide off. Flatter than that, and incoming waves will not break properly on the face. The angle is not an estimate. It is a calculated number from physics. Here is a detail that explains how precise this entire process is. When a buried boulder deflects a 12-meter sheet pile sideways during driving, the whole wall alignment is destroyed at that point. The fix is to pre-drill the boulder, crush it, then drive the pile straight through the cleared hole. Clean. No compromise. Because that steel sheet pile wall fights the retreating wave, not the arriving one. Backwash, the water rushing back out to sea, is what pulls foundation sand away and destroys walls from below. The engineers understood this from studying the 2011 failures. Fill material goes in at 300 millimeter lifts. No more, no less. Too thick, and the compactor machine cannot reach the bottom of the layer. The result is loose soil underneath that looks fine but is not. Every layer gets tested for something called Proctor density. The target is 98%. If you press your foot on 98% Proctor fill, nothing moves. At 85%, that same fill sinks 300 millimeters per day. The inspector can shut down the entire job if a layer fails the test. And inside every section of the wall body, geotextile reinforcement layers run horizontally, working the same way rebar works inside concrete, but for compacted fill. There is also a clay core, running through the wall. That clay is the wall's internal waterproofing. It stops water from soaking through the wall body during a long wave event. One night of heavy rain caused 600 millimeters of slope to slump on one section. The entire section was rebuilt from scratch, and a drainage pipe network now runs inside every embankment, so water pressure never builds up behind the face. Once the wall reached 10 meters, thousands of concrete panels began going on. These are not decorative. Each panel weighs 7 tons. Every hairpin bar connecting a panel to the crown wall above must be present. One missing bar breaks the structural connection. The concrete used is self-compacting, meaning it flows around every bar on its own, leaving no voids. The face must be perfectly flat before any panel goes on. One bump creates a stress concentration point. Under tsunami force, stress concentrations are where failures start. Every panel is tap tested after curing. A solid ring means good concrete. A hollow sound means the panel goes to the crusher. Each panel is worth around $800. It still gets crushed. Because a bad panel on a tsunami wall is not a cost issue. It is a life issue. The panels travel on narrow Japanese coastal roads. A flagman stands at every junction. The panels are set onto a bed leveled to within 5 millimeters. A hump of even a few millimeters cracks the corner of a 7-ton concrete panel. That face must hold for 100 years against repeated tsunami impacts. The joints between panels have rubber water stops. When the rubber gets wet, it swells. The bigger the wave, the tighter every joint seals itself. That is a passive system. It requires no power, no sensors, no human action. It just works. And on a curved coastline, straight panels would leave 20-millimeter gaps at every joint. Water forces through gaps and undermines the foundation below. So engineers made 37 unique panel shapes using C-machined molds. Every gap closes to 0. The crown wall at the top has a nose shape. That nose throws any water that tops the wall back outward, away from the land side. One design detail protecting thousands of people. What I find interesting is that it took studying previous failures to understand this. Backface erosion killed the old walls. So the new crown was specifically designed to redirect overtopping water. Not stop it, redirect it. Behind the wall panels, the armor layer on the seaward side uses tetrapods. These are 4-legged concrete shapes weighing 32 tons each. They are not placed precisely. They are dropped. They find their own stable position through controlled chaos. The gaps between tetrapods are not weak points. They are the mechanism. Water flows through the gaps. Energy spreads out and disappears. 1 liter of water fully absorbed by a tetrapod layer sounds manageable. Now multiply that by 50 million tons of tsunami water. There is an equation for calculating how much armor weight you need based on incoming wave energy. Engineers used it to specify every single tetrapod size along every section of this wall. Below the waterline, tetrapods pile up where no one can see them. Sonar imaging shows what divers cannot reach. 3 lines of defense sit in front of the main wall: a rubble mound, a sheet pile toe, and the tetrapod armor layer. The tsunami is supposed to exhaust a huge amount of its energy crossing all three before it ever reaches the wall face. Then there are the gates. This is the part that concerns me most when I think about it. The wall has 443 gaps. Every river mouth, every harbor entrance, every road crossing is a gap. Each one is a potential failure point. Each one has a gate that must close before a tsunami arrives. The window for closure is 70 seconds from the moment the alarm sounds. A seismic sensor triggers automatic closure the moment an earthquake begins. No human needs to push a button. The gate begins moving before the shaking stops. Each gate weighs 50 tons. The clearance between moving gate and frame is 15 millimeters. If one of 14 seals on each gate leaks even 40 liters per minute through a 2-millimeter gap, under real tsunami pressure, that gap grows to 20 millimeters and the gate fails completely. Engineers ground 2 millimeters off one seal. Retested. 0 leaks. 3 hours of machining to save a whole town. One gate type covers entire river mouths. A 22-meter steel curtain stored open at the top drops by gravity when the alarm fires. Gravity, not electricity, not hydraulics, because power fails during earthquakes. Gravity does not fail. All 443 gates closing simultaneously takes 4 minutes and 20 seconds from one command room. Japan drills this every single year on March 11th. On cliff sections, there is no beach. The wall goes directly into rock. Rock bolts go 2 meters into basalt. Concrete is sprayed at 100 kilometers per hour, which bonds to rock better than poured concrete does. The cliff and the wall become one structure. The tsunami hits concrete, bonded to shotcrete, bonded to basalt. 3 materials, one face, nothing moves. Offshore, a submerged breakwater sits 200 meters from the main coast wall. Its job is to trip incoming waves before they reach the main structure, reducing their energy before the real fight begins. The breakwater at Kamaishi was rebuilt even stronger than the world record it previously held. Confirmed. Always build back stronger. Every wall section was tested in a wave tank. Some results were unexpected. The engineering teams adjusted based on those results. Sensors are embedded inside the wall itself. Engineers watch it move, breathe, and settle every day. 14 millimeters of total settlement across 400 kilometers of coastal sandy ground over 2 years. That result is, to me, a number worth repeating. 14 millimeters on sandy coastal ground over 400 kilometers. Exceptional. A 7.4 magnitude earthquake hit during construction. The sensors fired. All 443 gates closed simultaneously. Engineers checked every section afterward. 0 cracks. 0 shifted tetrapods. That was not a simulation. That was a real earthquake, testing a real wall. And it held. The carbonation depth of the concrete is measured at 2 millimeters. That means the steel reinforcement inside will not see sea air for at least 100 years. The independent inspector can fail any section and order full demolition. All 440 contractors work under that pressure constantly. The inspector answers to no one on site. When the last section of wall was complete, a helicopter flew the full 400 kilometers and photographed every meter. What those photographs showed will inform coastal engineering decisions globally for decades. The staircases built into the wall are not scenic overlooks. They are evacuation routes, designed using crowd flow science to move maximum people upward in minimum time. People now cycle along the top, walk dogs, run in the mornings. The wall became part of daily life. What I understand now, after going through all of this, is that this wall is not just concrete. It is accumulated knowledge from 20,000 deaths. Every design choice came from studying what failed and why. The filter layers, the 98% compaction standard, the 70-second gate closure, the gravity-driven drop gates, the curved panels with zero gaps, the crown wall nose, the back face drainage system. None of those details exist without the 2011 disaster teaching engineers exactly what an ocean can do to a wall. This wall was never designed to stop a wave the size of 2011. Engineers confirmed that. What it was designed to do is buy time, slow the water, reduce its energy enough to give people those extra minutes to reach high ground. The engineering I found most interesting is this. The goal was never perfection against the worst case. The goal was maximum survivability when the worst case comes again. So for me, the main thing is this. Japan did not build a wall because they thought they could beat the ocean. They built a wall because they know the ocean is coming back, and they want more people to still be alive when it arrives.